Your producer is fast, your consumer is slow. No one told the producer. That's not a configuration problem, that's a design gap. And if you have an unbounded queue anywhere in your system, you have a crash waiting to happen. You just don't know when. Today we're talking about backpressure, the mechanism that closes the loop between a fast producer and a slow consumer, the three patterns for implementing it, and the design decision that turns a 40-minute silent crash into a graceful degradation. A video processing platform. Uploads triggered a processing job. Thumbnail generation, transcoding, metadata extraction. Each job pushed to an in-memory queue. The consumer worked through the queue at roughly 100 jobs per minute. Fine for months. Then a marketing campaign launched. Upload rate spiked to 1000 jobs per minute. The consumer was still running at 100. The queue grew at 900 items per minute. There was no bound, no alert on queue depth, no 429 to callers. The queue just grew. After 40 minutes, the queue held 36,000 items, each holding a reference to a video frame buffer. Memory exhausted. The process crashed. All 36,000 pending jobs were lost. The code change was small. Set a queue bound of 500. Return HTTP 429 when the bound was hit. Callers could retry with exponential backoff and jitter to avoid retry storms. The system now degraded gracefully under load instead of crashing silently after a 40-minute lag. The code was never the hard part. The design decision to bound the queue at all was what changed everything. There are three patterns for implementing backpressure. Most engineers reach for only one. Pattern 1, drop, also called load shedding. When the buffer is full, reject new work immediately. Fast and lossy. The producer gets a signal, request rejected, but some work is permanently gone. This is the right pattern for high volume, low value work, metrics, logs, analytics events. You don't need every log line, you need the system to stay alive. The industry term for this is load shedding, intentionally dropping work to protect the system. Pattern 2, buffer with a bound. Accept work into a bounded queue. As long as the queue has room, work enters and waits. When the queue hits its limit, new work is dropped or the producer blocks. The critical word, bounded. An unbounded buffer is not backpressure, it's deferred failure. The bound is what creates the backpressure signal. Queue depth becomes a real metric. Slowness becomes visible before the crash. Pattern 3, block the producer. When the consumer is full, pause the producer entirely until capacity is available. Lossless, no work is dropped, but it introduces latency back into the producer. The producer can't move forward until the consumer makes room. This is the right pattern where every item must be processed. Payments, order events, audit logs. You can't lose a payment processing job. Here's what the failure looks like without backpressure. Producer at 1000 per minute, consumer at 100 per minute. Unbounded in-memory queue. The queue grows at 900 items per minute without limit until memory exhausts and the process crashes. All work in flight is lost. Here's what the same scenario looks like with backpressure. Same producer, same consumer. In-memory queue bounded at 500. When the queue hits 500, the producer receives a 429. The producer retries with exponential backoff and jitter to avoid retry storms. The queue stays bounded. The consumer keeps working. The system survives the spike. The math didn't change. The load didn't change. The bound is what changed everything. Backpressure makes slowness visible. Without it, a slow consumer is invisible. Work accumulates silently for 40 minutes. Nothing alerts, nothing 429s. The first signal you get is a crash, and by then, all the work in the queue is gone. With backpressure, the producer sees the signal immediately. 429 seconds, blocked writes, timeouts. The problem surfaces at the boundary, where it's fixable. not in a crash 40 minutes later. This is why blocking is more honest than crashing, but only if your system can tolerate the added latency. A blocked producer is a system telling you it's full. A crash process is a system that ran out of time to tell you anything. The caveat? An unbounded block can exhaust your thread pool just as surely as an unbounded queue. Block with a timeout. Always. That in-memory queue is just one instance of a universal pattern. The deeper principle, every producer-consumer boundary needs a capacity signal. This isn't a new idea. HTTP has 429 and 503. TCP has flow control. The receiver window tells the sender how much buffer space is available. Kafka has consumer lag, visible queue depth that operators can alert on. Unix pipes have blocking writes. A write to a full pipe blocks the writer until the reader consumes. Every well-designed protocol already implements backpressure. If your internal system boundary doesn't have one, you've designed a gap. 3 things to check before the next spike. 1. Find every queue in your system and check whether it's bounded. An unbounded queue is a crash waiting to happen at an unknown time under an unknown load. Set a bound. It doesn't matter what number you pick. Start with something conservative and tune it. The bound forces you to decide what happens when the queue is full. Drop, block, or 429. All 3 are better than a silent crash. 2. Add a capacity signal at every producer-consumer boundary. For every place where work is handed off from one component to another, ask, what does the consumer send back when it's full? If the answer is nothing, you're missing backpressure. HTTP 429 with a retry after header is the standard pattern. Use it. 3. Make queue depth a first-class metric. Queue depth is not an implementation detail. It's a leading indicator of system health. A growing queue depth tells you a consumer is falling behind before it crashes. Alert on it. Put it on your dashboard. Respond before it hits the bound. Find the fastest producer in your system and ask, what happens when its consumer slows down? If the answer is the queue grows until something breaks, you're missing backpressure. One action today. Find one queue in your system. In-memory queue, message broker topic, task queue, anything. Answer 2 questions. Is it bounded? And what happens when it hits the limit? If you can't answer both, that's your next engineering task. Next, day 5. Queue mental model. A bounded queue is the backpressure buffer. Next, we go deep on what a queue actually is, how it behaves under load, and the mental model that makes queue-based systems predictable.